The bugs we're talking about today are really fun for a couple of reasons. One, they're super low level, it's the name of the channel by the way, and two, the way you exploit them is kind of like what you see in those spy movies. Right, where you stick like a bad USB stick or like a bad SD card into a thing and it pops the device. And I actually got it to work sort of on my Flipper Zero. We'll go into that here in a minute. What we're talking about is unpatched flaws discovered in the file system code bundled into millions of embedded devices. So if you're not really aware of how file systems work, right, there are different kinds of file systems like NTFS or FAT is another one, exFAT in particular for this video. And to actually interact with a file system, you have to have some kind of code that knows how to parse and read and present the files in that file system. Now, this library in particular is called FATFS. It is a generic FAT file system module, and you'll notice by the very Web 1.0 look of this that it's very old, okay? This is an old file system implementation of both FAT and exFAT for very, very low-level devices. Again, that is the name of the channel. So when I'm talking about low-level, right, what do I mean? I don't mean like a Linux device. I don't mean like an IP camera like this, because this runs Linux, and Linux has their own implementation of FATFS that is not this version. What I'm talking about is like super low level stuff like this, like microcontrollers, right? This is an STM32F7. This is vulnerable on a lot of the STM lines, and the reason is kind of interesting. So the way that you actually, trigger warning, go and make code work on these STM devices is you have to use this toolkit called STM32Cube IDE. You don't have to, but it makes the process of assigning pins to different functionality and generating code for the IP stack and the file system a lot simpler, okay? The way that these IDEs work is they go and they pull code that already exists off the internet, like the lightweight IP stack for maybe a TCP IP stack for your embedded device, and they also, point of this video, happen to use the FATFS file system here that is written by elmchan.org. I have literally no idea who this person is. If you want to learn more about how to implement this stuff, I have this tutorial that I found. I'll put a link in the description below, but basically it shows like, hey, if you want to be able to use an SD card on your STM application, you have to make it like this. And you'll see that there's FATFS middleware. It's kind of this blob that's just ignored. Third-party library referring to FATFS, right? In particular, what this applies to is these Flipper Zero. These bugs exist in this device because the Flipper Zero at the end of the day is just an STM32W series, W for wireless, right? For the 433 megahertz and sub-gigahertz antenna. And so this bug applies here too. Now I keep saying this bug. What are the bugs? Now the bugs were found and disclosed by this company called RunZero. RunZero, I think recently acquired by Accenture, but it's founded by the person HD Moore. HD Moore, if you're not aware, is the inventor, the originator of Metasploit, right? Like kind of the OG learn to hack, learn to exploit platform. And so they disclosed a variety of vulnerabilities, a variety of integer overflows, stack overflows. We're going to go into this one here in a minute. It's very funny. Long file name overflows, unsigned subtraction, etc. I'm not going to go into all these bugs. There's a ton of them. But the problem that HD Moore kind of highlights here, that RunZero highlights, is one, the reason why these bugs are so bad is kind of what I highlighted in the beginning of the video. All you have to do is take a FAT file system that is corrupted in a way that exploits the vulnerability in how this library parses the data, and plugging in the disk and having the OS or the system scan the FAT file system is what exploits the bug. That's it. This is literally like circa 2007 Windows XP, bad hacker drops USB stick at the Stuxnet factory, right? Like that kind of shit. Like that is the way that this bug would be exploited. And guys, it's no secret that big bugs like this can lead to big hacks. And that's why today's video is sponsored by Flare. Flare is an identity-focused threat intelligence system that allows you to see if your company's credentials are being talked about on the dark web. Flare is actively scooping up threat intel from a variety of sources like 22,000 Telegram channels and hundreds of millions of Stealer logs. Now with this data, you can put in identifiers about your company through either their identifiers dashboard or easy integrations like their Entra ID. I like this one in particular because you're able to integrate either Entra or Okta or just basic custom webhooks so you can pull in identifiers from your current systems. And from there, what you get is alerts when certain identities get compromised. So here I have an account that I did kind of a little test run on, and it sent me an email automatically when these credentials came up in their systems. Then I can go and remediate that issue as fast as possible. I think I've seen the quote from CrowdStrike that once an attacker gets in, it takes only 36 minutes for them to compromise their credentials in that network, and it takes an organization, a big, bureaucracy, upwards of 48 hours to respond. If you get notified when these kinds of things happen, you can dramatically reduce that time. Also, Flare has recently added ThreatFlow. It is a threat intel feed that is curated based on the events of Flare is picking up. The offer to try this for free expires, I believe, in 3 days when I'm recording this. So if you want to get in, try it now. Anyway, if you're interested in staying ahead of hackers in cyberspace, check out Flare. Thank you for sponsoring the video, Flare. Let's get back to it. And again, it has to be a code base that uses this implementation of the FAT file system. But, even then, it's not unlikely that these still exist in the IT, OT, right? Like the power plant world, the water management world, right? And what's so scary about this is these systems rarely get updated. They're very hard to update. So if this code exists there now, it's unlikely it won't exist there in the future. So what are the bugs? We keep saying the bugs. What are the bugs? Well, one of the bugs is an overflow in the get volume label, right? So when you have an SD card, I'm going to try to show it to you real quick if you get in focus. This represents a file system, and that file system is basically, it lives inside of a device, and that device has a volume label. It is the name of the thing. And as I highlighted before, there is a buffer overflow in the parsing of the get volume label. So the library exposes this get label function, and you use this get label function to get the label of the volume you want to look at, right? And so what you'll see here is we have the device, the drive number that tells you like which device are we talking about, and then we have the label output. So you give it the path to a drive, and it will output the label to this tcar pointer, right? And what it does here is we have this directory here, and what we do is we mount the volume, we read the label into a structure locally, and then what we're going to do is we're literally just going to do this very long for loop where all we're doing is loading a word from that directory, and then we're going to put it as UTF, so a 16-byte code, UTF-16 encoding, at the address of the label offset by the destination counter. That is the entire loop. What you will notice here is there is no length check. We are not checking against some end value that determines that we've hit the end of the label buffer. So this effectively is a stir copy that lands in label. So the user, the consumer of this API, does not have the ability to say, hey, by the way, can we stop at 64 bytes? And so unfortunately, Flipper Zero, the device here, uses that file system. When you plug in an SD card into this device, which I'll show you here in a second, it crashes the device. And as Run Zero says, the problem here obviously is that any physical access to this device or a device where this is vulnerable leads to a jailbreak. So a lot of the times these very, very, very embedded devices, because of like the hardware limitations and the software limitations, don't have modern mitigations like ASLR, right? Which randomize the location of binaries so you don't know where to exploit, or NX, where you can't execute certain pages that are writable at the same time as executable, right? These devices that not only don't get updates very often, don't have basic protections, okay? So by this bug existing, it's very hard for this to get mitigated by the industry. By the way, HD Moore actually published some proofs of concept if you want to test this thing locally on your own device. It's called Vuln's 2026 FAT FS Chance. I'll put that link in the description below. I'm pretty sure a lot of these bugs were found by AI, by the way, just based on the way that the markdown files are named. Perfect. Yes. Now. Time to trigger the exploit. So you see, we got a bus fault here because the exploit overwrote the program counter, and I returned to OX41414141. That's it. I made a video where I describe how AI and kind of why AI is so good at finding bugs. And you can find that video right here. Go check it out, and we'll see you in the next one. Bye, guys.